So today we're going to be talking about dual beam, positive filtering, non-dispersive IR. So I'll just load up a picture and we'll start drawing the actual analyzer. The first two things I'm drawing are the source, so an incandescent bulb would be the source for IR, and we have two sources because we have two beams. The next thing I'm drawing here is the sample cell. This is what contains the sample, so our sample would be flowing through the sample cell. The next piece is the filter cell. The filter cell is what we use to filter out the signal from the chemicals that interfere. We have a reference cell. The reference cell is for the reference beam, and it contains a gas that doesn't absorb IR, usually nitrogen. The last piece is the detector. The detector contains the gas we want to analyze, making it a specific detector for that gas. The last thing that we need to add here is a chopper to chop between the two beams. So that will either allow the light beam to go through the reference or through the sample and the filter cell. We'll look at a practice question to see where the gases should be going. So label the location of the gases in an NDIR setup to measure ammonia. The interfering gas is water. So we'll just figure out where each of these gases go. So we're measuring ammonia and the interfering gas is water. So first of all, the sample holder contains all the gases. So it just has a mixture of gases like ammonia, water, and anything else that might be in the sample. There's likely some nitrogen in the sample, all the other gases. So it just contains a mixture. The detector contains the gas we want to measure. So in this case, it's ammonia. And the filter cell contains the gas we want to filter out, in this case, water. The last gas we need to label is the reference cell, and that always contains, or almost always contains, nitrogen or something else that doesn't absorb IR. The next thing I'm going to talk about is what the signal would look like coming out of each path, so the reference path and the sample path with both zero and span gas. On the left-hand side of the page, we have zero gas in the sample cell in both of the sample cell compartments. So zero gas will be in both of those compartments. On the right side, we're going to have span gas in both of those compartments. So the left side of the page, zero gas, and the right side, span gas. The next thing we're going to draw is the chopper. So the upper portion of the page is going to have the signal open to the reference cell. So the light path is going to go through the detector from the reference. And the bottom part of the page is going to have it from the sample cell, and that's going to be for both sides of the page. So first we're going to look at the reference beam in the zero gas. The reference beam travels through the reference filter, or not filter, just the reference cell. And just travels straight through. So you can imagine a very high amount of transmittance. So if our plot on our graph at the bottom, the left side of the plot is transmittance, very high transmittance. So we'll draw a line across. And that's going to continue until we flip to the other, chop the other beam. So now we're going to look at the beam going through the sample cell. Because we have zero gas in the sample, not any light is going to be absorbed by the sample. However, when it hits the filter is going to absorb some of the light. So we're going to have a little bit lower transmittance due to that filter cell. So we'll draw a line with lower transmittance. And that's due to the filter. Now when we flip back up to the reference gas will be back at 100% transmittance. And when we flip back to the sample path, that's going to be absorbed by the filter cell. So we have a step function, it looks like, where we're flipping between the two beam paths. Next we're going to move over to the span gas. So the span gas is going to have a high concentration of the gas we want to measure in both cases. So first we'll look at the reference beam. The reference beam is going to look just like the zero gas because it's not touching that sample cell. And then we're going to look over at the actual sample beam going through the span gas. In this case, the span gas is going to absorb some of the light. So we're going to have lower amounts of light in the span gas. And the interference filter is also going to absorb some light. So we're going to have quite low transmittance coming through. Once the light beam gets to that detector, the light's been absorbed by both the sample and the interference filter. And then if we flip back to the reference filter, we're going to be back to high transmittance. And when we flip back down to the sample filter, or sample and the filter, we're going to have low transmittance again. So our step function is going to look bigger. So the difference between the reference filter, the reference beam path, and the sample and interference beam path, this difference is what's going to tell us our concentration. So a small difference indicates a low concentration, and a big difference indicates a big concentration. So as the concentration increases, the amplitude of that step function increases.